Record. Okay. Now, in a broad sense, there are basically two types of energy that we're kind of concerned with. There's what's called potential energy and what's called kinetic energy. You ever heard of these? Anybody heard of those two types of energy? A few of you have. Okay, yeah. So there's basically two types of potential energy, and then there's kinetic energy. Okay? Now, all the behavior of matter is driven by energy, which is why it's so important. Okay, so the reason that some chemicals react and make solids or make gases, or the reason anything happens in the universe is because of energy. The reason things grow or change or heal or bleed or change colors or explode, whatever it is, it's always driven by energy. So we really have to understand the energy component as well as the matter component around us. Okay. So yeah, in chemistry we're going to spend a lot of time on energy, right? So heat and changes in temperature and changes in what's called enthalpy and entropy, those little things. And how does all the energy changes drive reactions to either occur or to not occur, or make some occur faster, or make some occur slower, all these different things. Okay, so there is a law called the law of conservation of energy that says that energy is neither created nor destroyed. So that basically means then that whatever total amount of energy we have right now in the universe is what we've always had, and it's what we always will have, okay? It's not changing. So energy is not being created, and it is not being destroyed, okay? However, though, the energy can be changed from one form to another. So you could take, for example, let's say it's thermal energy, and you can change thermal energy into like electrical energy. Or you can take nuclear energy and turn it into electrical energy, or things like that. You can change energy into different forms, but you can't actually just make energy out of nothing, and it can't just disappear into nothing. Yeah, do you have a question? Okay. Yeah, okay. So, and you can also transfer it between objects, right? So like when you're playing pool, let's say, you're playing pool or something like that, and your cue stick, your cue stick smacks the cue ball, and that cue ball hits another ball. Well, you're transferring energy from the stick to the cue ball, from the cue ball to the next ball. Right? So you're transferring energy, but it's not just being created out of nowhere, right? It's not. Okay, so energy can neither be created nor destroyed. Okay. So I'm going to skip this. We don't have time, but. So what is potential energy? Well, the potential energy is basically it's kind of energy then that is stored up. It's stored up for later use. So you have the potential to do something with it, but you're not actually doing anything with it yet. Okay, so it's all kind of there and stored up. And normally there's one of two ways that you get potential energy. The first is based off of the object's position. Okay, so where it's located. And the second way you get this energy is based off its composition. What is it made of? Okay, so what kind of atoms are involved? What kinds of bonds have been formed? So these two things then are the storehouse of the potential energy. So I'll give you an example. Let's say you have a big boulder and it's sitting up way up high on a hilltop, right? So it's not doing anything right now up here on this hilltop. On the hilltop, it has potential to do something, right? If you give it a push, well, then it would begin to roll down the hill, right? But it's not doing anything right now. But based on its position, it has the potential to do something, okay? And the other one I said is the composition. So we'll see that is based off, again, of the way things are made. So for example, let's say if it's a gasoline or coal or something like that, right? So gasoline itself is not doing anything. It's not doing anything right now, right? The gasoline itself. But based off the carbons and the hydrogen structure, the way it's put together, its composition, it has the potential for that gasoline, though to be turned into, heat energy, electrical energy, mechanical energy, things like that. Yeah, so it's based off its position or its composition. Okay, here's a few examples, right? So water behind the dam. Okay, so right now, this water here, it's all built up, but it's not doing anything much yet. It's all kind of, stored up there. But if the dam were to break, well, then it would all begin to rush out, and then you would see the kinetic energy, right? So you would change it from the potential into what's called the kinetic energy, or the energy of motion. Or let's say you have a spring, right? So it's a nice cold spring, it's been compressed down. Okay, Oh, okay. So based off its position, then it has the potential to do something. Right. So once you release it, then it will go boing, right, and it'll change then. Okay. Or like I said, the bonds, and like in gasoline, bonds in food, coal, things like that. Now the kinetic energy, as I gave you a little hint, is the energy of motion. So now it's actually doing something with that energy. Something's happening now with that energy. Okay, so things are going on. So any object that is moving has some kind of kinetic energy. Right, so you're walking, like if you're walking, or a car is driving, or you throw a baseball, whatever it is, all those have kinetic energy. Okay? So now, like I said before, so once the water goes over the dam, well, now it's actually moving, right? It's the energy of motion. So that's kinetic energy. That's a different kind. Okay, like I said, or swimming, like I said, running, driving, whatever like that. Anything to do with motion, right? You're working out. So, or now if you're burning the gasoline, right? So it was stored up in the gasoline, but now you're actually changing it into energy of, like I said, heat energy, electrical energy, power in a car maybe, or whatever it is, right? So all kinds of different energy we can get out of it. So real quickly, pull out your hand out there, and let's just have you take your best guess at A, B, C, and D. Are these potential energies or are these kinetic energies? What do you think? So just real quickly, yes, write down your guess, and then we'll discuss it here with the neighbor in a second. So, yep, take a guess, and then talk it over with your neighbor to see what you guys think. Should be pretty straightforward, I think. But okay, well, we'll talk it over. Somebody can say, see what you get. What'd you get for A? Potential kinetic. B, potential kinetic. C, D. Talk it over. Okay, well, what's the first one? Rollerblading. Yeah, well, that's motion, right? Things are moving, right? Right. The person's moving, the skates are moving, so that's definitely kinetic. How about a peanut butter and jelly sandwich? Well, it's not actually doing anything, right? So it is potential, has potential. But in the peanut butter and jelly, though it's locked up in the bonds of those chemicals, all the energy, right? Right, and the fat and the protein, the carbs, right? It's all locked up in those bonds. How about when you're mowing the lawn? So that's motion, right? So things are happening, things are moving, that's kinetic. And as I already mentioned, with the gas in your gas tank, of course, it's stored up, right? So it has the potential to do something once you actually burn it. Okay, good. Well, heat. I want to discuss heat. So heat, sometimes also called thermal energy. Okay, so it's a little subcategory of the other two kinds. And heat is really associated with the motion of particles. So here's a question for you then. Well, why are things hot? Why are things cold? Well, the reason things are hot or cold is really it's all about the motion of the particles. We'll see. So that's why hot things feel hot or cold things feel cold, is based off the motion of the atoms and the molecules in them. Okay. So in general, the faster the particles, the atoms and molecules in it that are moving, the greater the heat or the thermal energy is going to be of that substance. So if you have, let's say, like a really hot skillet versus a cold skillet. Well, the hot skillet then, all the atoms and molecules in that skillet are vibrating at a much faster rate than the ones in the cold skillet. So heat thermal energy is based off the motion of particles. Okay. Okay, so here's a little delicious, horribly for you Totino's pizza. I used to live on these in college. These things were 99 cents back in the day. And so right now it's frozen, right? So when it's colder, it means they're moving slow, right? So the atoms are moving slow. And you take it out, put it in the oven, heat it up, and what do you actually do? We actually begin to make them move faster. And that's all that heat is you are imparting energy and you make them move faster, faster, faster. Okay, so now a unit we actually use to measure the quantity of heat is called the joule. That's named for a famous English scientist named James Joule. Did a lot of things with heat and energy. He actually did the law of conservation of energy as well that I mentioned earlier. That was his little creation. So James Joule was the man what was the man that did figure out that yes, energy can be converted from one type to another, but again, it's not being created or destroyed. You're just transferring energy from one type to another. This is a picture I took, by the way, in Manchester, England. First at the City Hall. It's at the City Hall. There, and statue is over here on the right. A guy named John Dalton. Statue is on the left. He's another chemist we'll see later on. So yeah, James Joules to the right as you walk into City Hall. John Dalton to your left. So anyway, so James Joule, and his unit is the joule, capital J. Okay, so joule is a way of measuring energy, and that is the official SI unit for energy, is the joule. Now, a more common one that you all heard, I'm sure, is called the calorie, right? You all heard of the calorie. We're all obsessed with counting calories or burning calories or whatever, right? So the calorie. So again, the calorie is another way of measuring heat or measuring energy in a sense. Now, a calorie technically it's the amount of energy required to increase the temperature of 1 gram of water by 1 degree Celsius, okay? So I'm just going to draw a little picture here. So let's say this is, try that again. Let's say this is an ice cube, or just a block of water or whatever, right? And this happens to weigh 1 gram exactly, okay? So if I were to heat this up on a stove or a flame or whatever, well, let's say it was at 20 degrees and I heated it up to 21 degrees. Oh, well, that took 1 calorie to do. So the energy it takes to raise the temperature of 1 gram of water, 1 degree Celsius, that's literally what a calorie is. Okay, the amount of energy to raise 1 gram of water, 1 degree Celsius. So if you want to raise up to let's say 10 grams of water by 1 degree, well, it takes 10 calories. Or if you want to do 1 gram of water by then 10 degrees, it's also 10 calories. Okay, so any combination of 1 gram and 1 degree is a calorie. Okay, so notice, by the way, that has a little small c calorie, and I'll show you the difference. There is a big C calorie as well. Okay, so in your notes, make sure you write small c, not big capital C. Okay, so 1 calorie is exactly defined to be true 4.184 joules. So make a note of that, put a little star by it, highlight it something, so you have that for later. So 1 calorie is exactly, again, defined to be true, okay, 4.184 joules. And of course, we are now experts with conversions, and we know you can write that either way, right? Either joules per calorie or flip it calories per joule, right? You can do it either way, depending on what you want to convert to what. Okay, 1 calorie equals 4.184 joules. Okay. So, of course, a kilojoule, well, kilo means 10 to the third, right? So kilojoules, 10 to the third joules, or 1,000 joules, right? A kilocalorie would be 10 to the third calories, 1,000 calories, right? Okay. Okay. So just real quickly, here's a little chart out of your book that I thought was interesting, so I thought I'd put it up here. This shows, some various energy amounts in those joule units. So you can see, okay, so how much energy then do you use to sleep for an hour? Well, even if you're sleeping, you actually use about 100,000 joules just to sleep. Okay? But 1 gallon of gas has about 100 million joules in 1 gallon of gas. So again, joules, right? Just different ways of measuring energy. Okay, so let's look at a little calculation here. Okay, so here's a Butterfinger. One of my favorite candy bars, by the way. That's why I put it up here. So a Butterfinger has 270 kilocalories of energy in it. Well, how many joules would that be? So we want to turn 270 kilocalories into joules. That should be pretty quick for us. Oh, I guess I'll do it with you, and you guys can help me. So 270 kilocalories. So I want to get to joules. What would I do first? Yes, turn it to calories. Okay, so let's turn kilocalories into calories. So what number goes on top or bottom, or what do I do here? 1 kilocalorie is how many calories? 1,000 or 10 to the third, right? Either way, right? Because kilo means 1,000, 10 to the third. Okay. Now I'm in calories, but I want to be in joules. So what do I do for that? Okay, yeah. So joules over calories, and how many of each? What did I tell you there to mark down, the highlight I told you? 4.84 joules is 1 calorie. Okay, good. So punch it in your calculators. Somebody tell me what you got. I don't have my calculator handy, so. What'd you get?
Rounded or?
Nah. Yeah. Give me a bunch of them first. 4 or 5.
1,129,680.
1,129,680. Okay. Joules. Okay. Well, let's check our sig figs, right? So 270. How many is that? Only 2, right? The N0 is not significant because there's no decimal. How about 10 to the third? Okay. How about 4.184?
That's exact.
4 exact. Yes. Remember, I said that is exact, right? Defined to be true. Exact. Defined to be true. I said it over and over. So how many should our answer have? 2. Okay. So what would the answer be? How would you round that off? What's the best way to show that with only 2 sig figs? Yeah. 1.1 times 10 to the 6. 1, 2, 3, 4, 5, 6 joules. Good. Awesome. What happened there? I don't know. Okay. Check something real quick here. I'm going to look at my slides real quick. I thought I had some. Okay. So let's look here. So now I said, right, the reason things are hot or cold is the energy of the molecules, right? Either they're moving like on a liquid or a gas, or in a solid, they're just kind of vibrating faster or slower. Okay, so that motion is what is creating the thermal energy. So when you measure the temperature of something, what you're actually measuring then is in a sense is the average kinetic energy. Okay, so when you're measuring the temperature, it's a measure of just the average kinetic energy. Okay, so how fast are those things vibrating on average? And then as they get hotter, well, they vibrate faster on average, or colder, they vibrate a little slower on average, or they move faster or move slower. Okay, so temperature is a way of measuring the kinetic energy. Okay, again, hotter, more random motion, right? More vibrating or swirling around a liquid or bouncing around off the walls on a gas, whatever it is. And colder, less motion, right? Right, slower vibration, slower bouncing off walls, things like that. Okay, now temperature is not the same as heat, though. Okay, so this is a little bit confusing at first. So you can have, for example, 2 objects that have the exact same temperature, but they have very different amounts of heat. Okay, so again, temperature, I said, right, is a measure of the average kinetic energy. But heat is really trying to measure how much energy is being transferred or being exchanged between 2 things. So I will give you an example. Well, actually, I'll give you 2 examples. Okay? So temperature just measures the average energy present. Heat measures the energy that was transferred between 2 things. So one example I have on the PowerPoint, and then I have one that's not on here. Let's say you have a cup of coffee, right? Oh, this is back into. Let me change modes here again, sorry. Maybe. Sorry. Give me a headache here. There we go. So the example here is, right, so I said, okay, so let's say you have a cup of warm water. Here's the cup and it has nice warm water in it, right? Well, now, if I throw an ice cube into this, make the ice cube blue, I guess. What happens? Well, heat is transferred from the warm water into the ice, right? So the heat's what's being transferred. right? So heat measures how much energy is being transferred from the water into the ice. Again, heat is not the same as temperature. So let me give you maybe a little better example that'll help explain why they're not the same. Let's say we have, clear this off. Let's say I have a little glass of water, and then I have a big giant bucket of water, okay? Okay, so both have water in them, right? And they're both really hot, okay? So they're really hot. So let's say they're both at 90 degrees Celsius. Are you with me? So both have the exact same temperature, but the big bucket of water has a lot more heat for it to give than the little cup of water does. Does that make sense? Does that make sense? Or to splice you with this versus this, you would get a lot more heat out of that bucket than you would out of the glass, right? So again, heat and temperature are not the same thing. Okay? Okay, so again, like I said, 43 times. Now, temperature is just a measure of the energy, not the exchange, but just kind of the measure. Okay, so I already showed you, right? So the cup and the bucket, the molecules are both moving basically at the same average speed. But the bucket had a lot more of it than there was in the cup, right? Okay. So there's 3 scales. You may have heard of at least the first couple. Of course, Fahrenheit and Celsius, we're probably all familiar with, right? So Fahrenheit's one we use here in America. Celsius, again, is the metric scale. And the third one that we oftentimes use in science as well is called the Kelvin scale. So I just want to kind of go through these real quickly. So again, mostly in science you'll see the Celsius scale, but you may also see the Kelvin scale depending on your job and what you're doing. So there's Fahrenheit, Celsius, and Kelvin. Now just real quickly, I want to point out that you notice it's degrees Celsius and degrees Fahrenheit, but it's not degrees Kelvin. Kelvin is a unit, just kind of like meters or pounds. Okay, so it's not degrees Kelvin, it's just how many kelvins, how many pounds, right? How many inches. It's just another unit. Okay, so yes, there is no little degree symbol for Kelvin, just FYI. Okay, well let's look here at the difference between the 3 different scales and see what we can figure out. So notice, okay, so here is where water freezes on the 3 different scales. Here's where water boils on the 3 different scales. So the difference on the Celsius scale, the one in the middle between where water freezes and water boils, is 100 degrees. Right, see that? So freezes at 0, boils at 100. Now, on the Fahrenheit scale, water freezes at 32 and boils at 212. So that's a difference of 180. All right? Agree with me on that? So, basically then, you can see then that the Fahrenheit scale is a larger scale of the terms of its increments compared to the Celsius scale. So basically then, a change of 1 degree Celsius is a change of 1.8 degrees Fahrenheit. Does that make sense? Can you see that? Or a change, let's say 10 Celsius would be a change of 18 Fahrenheit. So the Fahrenheit scale is about 1.8 times bigger, larger than the Fahrenheit scale. I mean Celsius scale. Can you reason that out? It's 180 to 100, right? So it's basically about 1 point. But notice on the Celsius and the Kelvin scales, those have the same increment. So between freezing and boiling for kelvins, that's also 100 degrees, or 100 units, actually not degrees technically. So a change of 1 Celsius is the same as a change of 1 Kelvin in terms of magnitude. Or a change of 10 Celsius, same as a change of 10 kelvins in magnitude. So if you go up by 1 Kelvin, that's the same as going up by 1 Celsius, or going up by 1.8 in Fahrenheit, right? You with me? So the Fahrenheit scale is a bigger scale in that sense. Now, you're also going to notice the way they start is a little differently, right? So I'm going to go back. All right, so I just showed that right there. Okay. Okay, but you also notice that 0 is different, right? So on Celsius, 0 is the freezing point. On Fahrenheit, the freezing point is 32. So not only is the Fahrenheit 1.8 times bigger, but it's also 32 higher, Can you see that? Can you see the difference there? So this is 32 higher. So basically then, the way it works when you transfer between Celsius and Kelvin is you're going to have to add 32, you're going to have to multiply it by 1.8. That's kind of the basic formula. So you're going to take that Celsius, you're going to make it 1.8 times bigger, then you're going to add 32 to it. So that's basically the equation for turning Celsius into Fahrenheit. So if you want to know Fahrenheit, you take the Celsius, multiply it by 1.8, right? So you make it bigger for the Fahrenheit scale. Then you bump it up 32. So that's where that comes from, just so you kind of know now. So Fahrenheit equals 1.8 times Celsius plus 32. Fahrenheit equals 1.8 times Celsius plus 32. Got that written down? Okay. And these, by the way, are exact. So the 1.8 is exact. It's not 2 sig figs. And this is exact too. The 32 is exact. Those are both exact. Okay. Now, how about doing it the other way? Let's say you had Fahrenheit and you wanted to find Celsius. What's a little bit of some basic algebra? So you'd have to subtract 32 from both sides and then divide both sides by 1.8, right? So you would wind up getting that when you were done. Fahrenheit minus 32 over 1.8. Okay. Hopefully the algebra is not too bad for you, right? So you got to subtract both sides by 32 and then divide by 1.8. Okay, have those two written down? We'll try them here in a second. We'll practice with a couple of those. Celsius is Fahrenheit minus 32, the whole thing over 1.8. Okay. Now Kelvin, oh, yep. Oh, still writing? Okay. Well, let's look at kelvins. Now you notice the Kelvin and Celsius had the exact same, basic magnitude of the scale, but they were shifted way off in terms of where they started at, right? Oops, that's wrong. What happened there? There we go. So what's the Kelvin scale? Well, again, kelvins is a unit, right? I said it before, so it's not degrees Kelvin. Now, the Kelvin scale is interesting in that its 0 point is called absolute zero. Okay, so its 0 then has been defined or set as the coldest possible temperature. So my question for you is, why is there a coldest possible temperature? Why can't you just keep on going colder and colder? Why is there a limit? What do you think? Yeah, what do you think, Brandon?
Absolute zero is the point where a particle stops moving.
Yeah, so all the motion stops, right? So I said earlier that the temperature is how much they're moving, right? So as they move slower, they get colder, and eventually we're gonna totally stop moving. And when they totally stop moving, I mean every last bit of motion to stop. That's the coldest you can get. That's absolute zero. So that's 0 Kelvin. So 0 Kelvin is the absolute coldest possible temperature. Which means then on the Kelvin scale, there's no negative numbers possible, which is a really nice thing. Which is a really nice thing then when it comes to calculation, because there's no negatives to worry about in the Kelvin scale. Because again, you can't go colder than the absolute coldest temperature. That's as cold as you can go. Okay. So that temperature is Celsius is negative 273.15 Celsius. Yeah, so we have never yet actually hit absolute zero. We have been very, very close in laboratories, but never actually got there. Even outer space is not quite that cold. So it's really cold. Yeah. So the difference between the Celsius scale and the Kelvin scale, you might notice in that chart, was 273. So 0 Celsius was positive 273 Kelvin. And 0 Kelvin's negative 273 Celsius. So they are different by 273.15 basically. Okay? So that means if you want to find Kelvin, just take the Celsius and add 273. Or they're going some more significant figures. You can add 273.15, depending on your significant figure needs. So yeah, so they're exactly the same magnitude, right? So no multiplying by 1.8 or anything. Just got to make them different by 273. Okay, so you have that one written down. So you have all three written down. You got the Celsius to Fahrenheit, Fahrenheit to Celsius, and now you got Celsius to Kelvin. Okay, so let's try a couple of examples here. So get out your hand out again, hopefully. So a person with hypothermia comes in, and their body temperature is 34.8 degrees Celsius. What is that temperature in Fahrenheit? So 34.8 degrees Celsius, we want to turn it into Fahrenheit. Okay, hopefully you have your hand up. I'm going to put a little whiteboard up here and work it with you. So we have 34.8 Celsius. We're trying to go to Fahrenheit, right? So what's the formula between turning Celsius into Fahrenheit? Well, temperature in Fahrenheit is what?
1.8 Celsius
1.8 times the temperature in Celsius, we said,
plus 32.
plus 32, right? Okay, so let's do that. So let's take 1.8 times 34.8 plus 32. So let me grab my calculator, I guess. And you guys can try it along as well. Okay, I got 94.64. Is that what you got? But, now remember, these are exact, right? These are exact. So really, the way it kind of works normally is however many decimal places your original number had, is how many decimals the converted number will have. So 34.8 had a decimal, so the Fahrenheit's going to have just a decimal too. So we normally round that off to 94.6. So we're looking at this number because the other ones are exact. Okay, good. Well, let's try the next one. Whoops, maybe. A pepperoni pizza is baked at 455 degrees Fahrenheit. What temperature would that be on the Celsius scale? So try that out. Help each other out if you need to. Work it out. And then after that one, go ahead and try C. Turn Celsius to Kelvin. And I will give you those equations, by the way. I should mention that on the test or quiz. Because you always have the equations. You've got to know how to plug them in and use them. Okay, so I will give you those on a quiz or a test. So I guess don't freak out by them. You just have to know how to use them. So talk it over. Help each other out. What'd you get? What do you think?
And then the other two.
That's not good. Let's do this first.
Now, there's a common calculator error on this one. You got to be careful of. You make sure how you enter it in. Else your calculator will lie to you. You can't just put 455 minus 32 over 1.8. That will not give you the right answer. Okay, let's try it out here. So again, the formula is Fahrenheit minus 32 over 1.8, right? But I'm saying you can't enter that in as like this on your calculator, all right? You can't do 455 minus 32 divided by 1.8. Why is that a bad deal? Because it only divides this part first, right? So it always does division first, then subtracts. So you got to do parentheses and then divide it by 1.8, or do the first part, hit equals, and then divide by 1.8. But you can't do it like this, else it will divide this by 1.8 and then subtract it from 455. So that one will not work. Okay, so what'd you get? What is it?
235.
235, okay. 235 degrees Celsius. And again, we'll just keep the same number of decimal places, right? So 455 had no decimals, so this one will have no decimals. Okay, well, last one. Just try the last one if you didn't yet. Celsius into Kelvin. Celsius into Kelvin. 37 Celsius is normal body temperature for most of us. So what's your body temperature in Kelvin going to be? So, it's the same temperature. It's the same change. If it was a change of 37, it'd be a change of 37. But what is the temperature now in Kelvin? There's a formula. There's a formula that I gave you.
Right.
So you take the Celsius and you do what to it? Add 273. So what'd you get? 310, right? Right. 310. Good. Good. I guess technically it should be 310 with a decimal point, just to keep the same places. One decimal. I mean, one's place, whatever. But okay, well, so that's just real quick and dirty. And again, there's more homework practice on that. So again, tonight, tomorrow, go on Mastering Chemistry, practice this stuff while it's still fresh in your brain. Okay, do some more examples with calories and joules and Celsius, Fahrenheit, different things. Okay, well, what is matter? Well, I said back on the very first day of class, I believe, that chemistry is basically concerned with the activity of matter. What does matter do? So we concern then with its characteristics, its composition, what it's made of, and then its transformations. So the way we can change it, do things with it, all about the matter. And then again, I just told you though that the reason these things happen is energy is driving them, right? So the reason, like I said, things explode, or the reason. Or the reason, I don't know, scabs form, or the reason plants grow, or leaves change colors, or whatever happens, because the energy is driving those changes in some way. Okay, so matter is anything that has mass and occupies space. So that is kind of the broad definition of matter. So anything that has mass and occupies space. So that's pretty much everything around you. Okay? Now there are a few things that maybe aren't matter, right? Either they don't have mass or they don't occupy space. Maybe you say, I don't know, like feelings maybe, right, or emotions, right? So so those kind of things are not technically matter. I mean, they matter, but they aren't really matter. Does that make sense? So yeah. But everything else you think of, right? People. Right, planets, right, the walls, the Earth calculators, the air around you, I mean, everything, right, has some mass. It occupies space. So, right, does that make sense? Even right now, like I was saying, the air around us, right? I mean, even if the air, they're really small particles, but there is, right, in the air around us, little tiny particles of oxygen and nitrogen and carbon dioxide that are really there. Any questions? Okay, good. Okay, yeah. So like I said, again, it's things you can see, like people, desks, but also things right that are invisible, right? Like I said, like air and gases, things like that, right? Things that are alive, things that aren't alive, right? These are all things that matter. So if it has mass and it occupies space. So how can we? Yeah.
How about sound?
Sound, I guess would not be matter. No, it would be then on the energy side of the equation. Okay. So it's either matter or energy. So how can we classify matter? Because matter obviously is a big thing, right? It's like pretty much everything. Okay, so as I was saying, in chemistry then, we want to try to classify things into their characteristics, is one of the things I said. So, all matter can be broken down into one of two things. Either a pure substance or a mixture. Now, pure substance is something that is composed of only one type of atom or molecule. So pure substance is something that's only made up of one thing. So it's pure gold, or it's pure water, or it's pure carbon dioxide. But it's not multiple things, okay? That's a pure substance. So it has a fixed composition, or you might call it like a constant composition. So again, it's not changing. It's not a variable changing composition. It's just pure gold all the time, or pure copper, or whatever it is. Now a mixture is just the opposite. A mixture is two or more different types of atoms, molecules, whatever it is you're mixing together. And this will have a variable composition. So let's say you had a mixture of like salt and water. Well, again, salt's a pure substance. Water's a pure substance. When you put them together, well, now you've created a mixture because you can vary the amount of salt to the water too, right? So you could have a solution, maybe it's 5% salt or it's 20% salt in the water. So it's two different things mixed together, and you can change the ratio of the two different things. Yeah?
No, water would be a pure substance even though it has hydrogen and
Good question. Okay, okay, good question. Yes, it is. Okay, good question. Yeah, so for example, like I said, gold is, but water also is a pure substance because it is just pure hydrogen and oxygen, but it's in a set composition, a fixed composition. It is always two hydrogens directly bounded to one oxygen, okay? It's set. It's not a mixture of some hydrogen and some oxygen just kind of mixed around in a gas. It is a molecule of hydrogens bonded to oxygen in a 2-to-1 ratio. Now, a mixture, though, yeah, might be a mixture of, let's say, we had hydrogen gas, which actually is H2, mixed with oxygen gas. So that would be a mixture because maybe it's 10% hydrogen and 90% oxygen one time, but then it's 50-50 the next time, or 40-60. So that's a mixture where you can change the composition of things. Okay, so yeah, an atom, or what's called a molecule, can be a pure substance. Like I said, so like salt water, right, is a mixture. Okay, so they are physically mixed, but they're not chemically combined the way they are like in water, let's say. So yeah, so get some water, you stir in some sugar, stir in some salt, and you can change the amount. Okay, so that's a mixture. Okay, let me write this up on the board. Because so matter, we can divide it into pure substances or into mixtures. Okay, so that's the first way to classify it. Okay, back up. What we kind of tell sometimes is a mixture. Then a mixture of substances. Then you could actually go back and you could actually separate them out into their components, just using some kind of a physical method. So, for example, if I had salt and water, right, salt mixed in water, well, how can I separate out the salt from the water? How can I get those two back?
Boil it.
Exactly. It's boil off the water, right? Now you have the salt left, and you collect all the water vapor as the steam. But if I have just, let's say, pure water, there's no way physically then to separate out the hydrogens from the oxygens because they are chemically bound together in a new molecule, a new form. Okay, well, one way then to separate pure substances is the two different classifications. We could do it as element. That's the first way. Now, an element are all those, all those things that are listed on your periodic table, of which about half or less you are learning the symbols for, right? So, element is a pure substance, and it can't be broken down into a simpler substance. At least you can't break it down simpler in like an actual laboratory, chemically or even physically. You have to put it in. Now you could typically do that a simpler than a simpler than like a nuclear chemistry or something like that, like nuclear reactors. But it's your everyday, lab or a factory. You can't just break things down simpler than elements. So yeah, once you get to hydrogen, that's it. Or once you get to gold or copper or aluminum or whatever it is, that's as simple as you can go. And it's an everyday, physical, chemical separation kind of thing. Okay, so there's no way to break it down any simpler. And again, like I said, right, all the ones that are known are listed on the periodic table. There's about 117 now, which I think you see on your table. 118. There was a little gap over here. It was just filled in, I think, like in the last couple of months, actually 117. It's just filled in. So, like I said, right, copper, right, lead, iron, all these different things. These are all elements. So that's one way to classify pure substances. The other way to classify them is in compounds. So compounds are where you take two or more elements, and now you combine them again in a fixed or a definite composition. So like water, right? So water, H2O. That is a fixed ratio of hydrogen to oxygen. And they are chemically bound together, and you cannot physically separate them out. Okay? Now, obviously, there are many, many more compounds in the universe than there are elements. Right? Many, many more compounds. So yes, we're just saying there's only about 118 elements. And of those, only the ones up through uranium are actually naturally occurring. So only on your table, the first 92 are naturally occurring. I'll write that, 92 naturally occurring. But there are many more than 92 things in the universe. I would think you would agree, right? There are bazillions of things, right? So those bazillions of things are all made up of different ratios of these 92 elements. Okay? So lots more compounds than there are. Well, why is that? Why not there some more compounds? Because most elements are very reactive, and they don't like being by themselves. They want to combine carbons to hydrogens, hydrogens to oxygens, sodiums to chlorines, whatever it is. They want to react. And we'll see then, as we go on in chemistry, the reason they want to react. They want to become then more stable, basically, normally is the case. They want to become more stable together than they were by themselves. Now, compounds, though, can be separated back into elements, right? But again, as I said now 4 times or so, elements can't be separated any smaller, right? So that's it. It's as simple as you can get. Unless, again, like I said, one little caveat is in a nuclear reactor, then you can shred them down into electrons and protons and things, maybe. But normally you can't do that kind of stuff in just a regular, everyday lab. So, water, right? H2O, that's a compound. That is a fixed ratio, 2-to-1 of hydrogens to oxygens of the two different elements. Sugar is a fixed ratio of 12 carbons, 22 hydrogens, and 11 oxygens. Sodium chloride is a fixed ratio, 1-to-1, sodium to chlorine. So again, those are compounds made up of 2 or more elements. Okay. Okay, this is one of the things that I really love about chemistry. Again, there are only 92 elements. Okay, think about this for a second. Everything you can think of, everything in your life, is only composed of 92 different elements, really. Okay, so this was a box of crayons, let's say. Everything around you, that's been created or drawn or colored, is only made out of 92 different colors, in a sense, right? Right? So all of the billions of things, like I said, people or planets or puppies or calculators or iPhones or hair, skin, glasses, whatever it is, shirts, clothing, desk, carpet, it's all made up of only 92 different elements. So notice, even here, right? So hydrogen and oxygen. This has hydrogen and oxygen. In your body, for example, is almost entirely 3 elements. Carbon, hydrogen, and oxygen. But your body has all kinds of different form and function, right? So you have eyeballs and skin and hair and nose and blood cells and hearts and livers and whatever, right? But they're all pretty much made up of only 3 different elements. So where the magic happens, then, in a sense, is the ratio of those elements. Okay, so how many carbons with how many hydrogens? And then how are they actually put together? Are they all put together? Let's say them, like this, or are they put together like this, or things like that, right? So the way put together totally changes its properties, its characteristics. So I will give you a big kind of a crazy example. So let's look at sodium and chlorine. Okay, so just pure sodium, the element. It is a solid. It is a shiny white metal solid, and it is crazy reactive with water. Okay, so you put it into water, and it just explodes and bursts into flames. And then let's say we have chlorine gas. Okay, chlorine gas isn't a gas, right? It's a gas. It's a green gas. It's super, super poisonous. It was used by the Germans back in World War I as a poisonous gas. Okay, so you take this solid, shiny silver metal that's very explosive, and you combine it with this super toxic, poisonous green gas, and you make salt, and you put it on your French fries, and you eat it. Is that the craziest thing ever? This is why I love chemistry. So you take an explosive metal, a poisonous gas, put them together, and now you can eat them all day long. So that is the crazy thing. So the properties of compounds, again, can be totally different from the properties of the elements, right? And again, it all comes down to whatever ratio you're using to those exact same elements. So again, as I was saying, right, in your body, there's probably 50 million different types of cells and things in your body, right? And they're all basically made up of carbon, hydrogen, and oxygen. But 50 million differences are how many carbons and hydrogens and oxygens, how are they connected, right? All that kind of stuff. So yeah, that's kind of the cool thing I like about chemistry. Now, mixtures, we can also break down mixtures into two different classifications. So, the first one we can call homogeneous, and the second one is heterogeneous. Okay, so there's two different types of pure substances, two different types of mixtures. Yeah. Now, a homogeneous mixture, sometimes you will hear it pronounced homogeneous, but homogeneous is the way I learned to pronounce it. Homogeneous versus heterogeneous. Homo, of course, you might know means, right, same, right? So a homogeneous mixture is the same throughout, okay? It's uniform all the way through that mixture. So it has the same properties all the way through your mixture. Top to bottom, front to back, left to right, all the way through. The same density all the way through. The same melting point, the same boiling point, the same, I don't know, whatever you can think of, color, the same smell is going to be the same all the way through that mixture. Okay? Now it is normally pretty easy then for you to tell a mixture if it is homogeneous because it looks the same. Okay, so you can look at your glass of water or your mixture, whatever it is, and you won't see floating chunks or different colors. It'll look uniform throughout. Okay, so it's normally like I said. So again, even visibly, you can normally tell. You just look at it; it just looks the same. So like salt water is normally homogeneous. Okay, so you have some water, like I said, and you have a little salt. You pour it in, and your water, and it's all stirred up. And now once it's all mixed together, it is the same throughout. It's the same saltiness, hopefully top to bottom, left to right, the same density all the way through, the same melting point all the way through, same boiling point, same color, whatever. Because as long as all the salt then isn't actually dissolved, right? So there's still chunks of salt floating around, well then it's not homogeneous at that point. But if it's all dissolved, that's homogeneous. Okay, air is another homogeneous mixture, right? So the air right now in this room is a mixture, an equally uniform mixture of nitrogen, oxygen, carbon dioxide, helium, argon, etc. Right? So it's the same all the way out. So, does that make sense? Right? So it is the same amount of, let's say, oxygen up here in the room versus the back of the room. Right? So they're all the same, right? All the way through the room. It's a uniform mixture. Okay. Heterogeneous are just the opposite, right? They are not uniform, right? So whereas homo is same, hetero means different. So they have different properties throughout. And again, you can normally tell what that is. Okay, so you will see chunks or floaties or layers or different colors or things like that, okay? It's pretty obvious at that point. So let's say we had now sand and water. Well, that's a heterogeneous mixture, right? So a mixture of sand and water, some of the bits of the water then we'll have a little bit more chunks of sand than others, right? Some will be sand free, and some will have a lot of sand. Some will have a little sand, right? So it's an ever changing mixture or ratio. Does that make sense? The difference? Okay. So here's our big flow chart we just wrote, right? So matter can be pure substances or mixtures, and those can be broken down into elements, compounds, or homogeneous, heterogeneous. Okay, so let's try a few guesses here. So take out your handout and take your best guess on, are these pure substances or are these mixtures? So take a guess, write it down, then talk it over with your neighbor, see what they think.